Hello, everyone. I appreciate you taking the time to join me today. We are diving into backpropagation as one of the most fundamental algorithms that powers modern artificial neural networks. Have you ever wondered how neural networks learn and improve with each error they make? The secret lies in backpropagation. So in this session, we will take a structured approach of understanding backpropagation, and next we will briefly explore the training process in artificial neural network. A crucial aspect of this process is mathematical foundation behind training. So we need to understand in order to grasp how artificial neural network optimize its performance. Following this, we will discuss the main challenges associated with backpropagation and corresponding solutions. Finally, we will summarize our key takeaways and conclusion from today's discussion. Let's get started. So artificial neural networks is in the category of supervised learning under the category of learning and AI. Neural network can be used for classification and regression. As you know, in classification, we try to assign data to discrete categories. On the other side, in regression, we try to predict continuous values. But how neural network learn from data? It's via training process. The training process starts after parameter initialization, and then it includes two phases of feed-forward and backpropagation. You already know how feed-forward works and how to calculate the error. So once we calculated the error, we need to update the network weights and biases. This is where backpropagation comes in. Backpropagation works by computing the gradient of loss function with respect to each weight and bias in our network. So this tells us how much each parameter contributes to the error and how to adjust each parameter in order to minimize the loss function using some optimization algorithms. So we use like gradient descent, Adam, RMS probe, or stochastic gradient descent in order to update our weights. Then we will repeat this process until we come to some stopping criteria. When the error is minimized below a certain threshold, when the loss function stabilizes, it means convergence, or when the maximum number of iteration or epochs reached. You already know how to present mathematically feed forward. So as a reminder, in feed forward, the process starts in the output layer, then we go layer by layer, and we pass through hidden layers. So we start from input layer, then we pass through hidden layers, and finally we come to the output layer. So in the hidden layer, the weighted sum of activation from previous layer is computed, bias are added, and activation function like ReLU, Sigmoid, Tanh are used in order to introduce nonlinearity. Then at the output layer, weighted sum is computed, and the activation function is selected based on the task. For example, if you have classification, binary classification, we can go for sigmoid. If you have multi-class classification, we can go for softmax, and etc. Then finally, we can have this one as double output or predicted one. So you know about loss function. We have different loss function for regression, for binary classification, and for multi-class classification. And the objective here is to minimize loss function. So here is the step-by-step error calculation in backpropagation. In the first step, we calculate the error as the output layer because we are going back, right? In forward propagation, we go from input layer to output layer. From backpropagation, we come from output to input. And in the first step, we go for the output layer error calculation. For a given neuron, like I at layer L, we calculate error, we show by delta. This is simply the difference between the predicted value and the actual value. So this equation represents how far off our model's prediction is from the actual value, and it is a starting point for adjusting weights in the network. Then we go for hidden layers. For the hidden layers, we calculate the error in a backward manner. We start from the second to the last layer and moving backward to the first hidden layer. Then we calculate the error using this equation. So this is the WL plus 1 is the weighted matrix connecting layer L to layer L plus 1. And this delta L plus 1 is the error from the next layer. Then we will do element-wise multiplication, and J prime Z is the derivative of the activation function applied to the weighted sum ZL. This process is repeated for each layer until we reach the input. So this will allow us to compute gradient needed for weight updates. The third step is gradient calculation. In this step, we calculate the gradient of cost function with respect to weights and biases. So here, del J is the cost function that measures the error of our network, and Wijl is the weight connecting neuron J in layer L-1 to neuron I in layer L. And this one, del J with respect to del Wijl is the gradient of cost function J with respect to the weight Wijl. So we use this one in backpropagation in order to update the weights. And M here is the number of training examples. So this AJL-1 is the activation of neuron J in layer L-1 for ETH. This is a counter for the training examples. And this delta ILE is the error term or backpropagated gradient for neuron I in layer L for the ETH training example. Finally, we have lambda here. This is the regularization parameter that controls the strength of weight decay, like L2 regularization. So for weights, the gradient is determined by the activation of previous layer neuron and the error from the current layer neuron. This tells us how much the weight need to be updated. So we do the same thing for the bias as well. Finally, we will update the weights here. Once we have the gradients, we update weights using these two equations, right? So here, this is the new weight, new bias. This is the old weights, old bias, minus this alpha is the learning rate. This alpha is used to control the size of the step taken in the direction of negative gradient. So in this way, we can produce new weights and new biases. But like any other process, there are some challenges associated with backpropagation process. Some of important problems are vanishing gradients, exploding gradients, overfitting. Then we have here learning rate selection, and we have also trapping in local minima. So I will briefly explain what are these problems and what are the solutions for each one. In this process of backpropagation, gradients that are used to indicate how much the loss function changes with respect to the weights can become either extremely small, that we call it vanishing, or they can become extremely large, that we call them exploding. So this vanishing and exploding makes learning difficult, especially in deep neural networks where we have many hidden layers. But why such problem happens? The first reason is because of the activation function. Activation function like sigmoid or tanh can saturate, and they lead to very small gradients. Another one is weight initialization. If you poorly initialize weights, we may face such problems. So the solutions here is, the first one is ReLU activation. Unlike sigmoid or tanh, ReLU introduces nonlinearity without saturating easily. And another one is weight initialization. Instead of random weight initialization, we can go for some initialization techniques like Xavier, Gullerod, or Hay initialization. Another solution is gradient clipping. This gradient clipping limits the magnitude of the gradient to prevent from exploding. The next problem is overfitting. Overfitting occurs when the model performs well on the training data, but it fails to generalize on new, or you can say unseen data or testing data. This means the model has essentially memorized the training data, including noise, rather than learning generalizable patterns. Why this happens? Because of complex models, or we have insufficient training data. The solutions, we can think of L1, L2, or elastic regularization. We can go for dropouts, randomly disable neurons during training to make the network rely on different connections, or we can go for data augmentation. The next problem is learning rate selection. Learning rate controls how much we adjust the model weight in response to the calculated error during backpropagation. But what should be the size of this step? If we go for high learning rate, it can cause optimization process to overshoot the minimum of loss function, leading to instability or divergence. If you go for a very low learning rate, it results in slow training and the possibility of getting stuck in local minima. So in order to do that, we can go for experimentation. We can start with a small learning rate like 0.001 for Adam and adjust it based on the training process. We can go for learning rate schedulers like in PyTorch and TensorFlow. We have some kind of this tool to do that. Or we can go for visualization. And what we do here in visualization, if we can look at the visualization of the loss curves, and if the loss fluctuates or escalates significantly, the learning rate might be too high. If the loss decreases very slow, the learning rate might be too low. An optimal learning rate leads to steady loss reduction. Another problem is trapping in local minima. So most artificial neural networks use non-convex loss functions, meaning the optimization process can easily get trapped in local minima. So the solution is we can go for momentum, we can go for SGD, stochastic gradient descent. So as you can see in this graph, when we start from this point here, if we go in this direction, we may go to global minima. But if we come to this direction, we come to the local minima. If we go for like a stochastic gradient descent, momentum, or maybe we go for adaptive gradient, like the RMS probe, we can see the better performance and get rid of the local minima. So in here, we can see different optimization techniques try to reach the minima. You can see SGD is very slow. Momentum provides inertia while descending the gradient. It is said that when we fall into local minima, we can get out of it with the power of inertia. However, as you can see, if the force is strong, it goes around when approaching the global minima. So, as a conclusion, backpropagation is a fundamental algorithm for training neural networks, and they enable our neural network to learn from data by updating weights and biases based on the loss function's gradients. It is crucial for efficiency training deep neural networks, allowing them to process large data sets and recognize complex patterns. By iteratively refining predictions through error correction, backpropagation drives continuous improvements, making it a key component in the success of deep neural networks. Thank you for your time and attention today. I truly appreciate your engagement throughout this presentation. If you have any questions, comments, or concerns, please feel free to reach out to me via this email provided here. Once again, thank you, and I look forward to hearing from you.